We're now looking at Euler's theorem to figure out the number of edges on the frame of this house. Again, this is pronounced Euler, not Euler. The formula is F plus V is equal to E plus 2. So we're going to find the number of faces and number of vertices and use that to find the number of edges. So in this case, if we look, we have a front and a back here. That's 2. And then we have 3 on this right side, 4 on top, 5 on top, 6 on the left, and 7 on the bottom. So that gives me 7 altogether. 1, 2, and then 3, 4, 5, 6, 7. Number of vertices, we have 4 on the bottom, and then we have 5, 6, 7, and 8, and then 9 and 10. So we have 10 there, and we're going to use that to find the number of edges. And here we have 17 is equal to E plus 2, subtracting 2 from both sides. E is equal to 15. And if we double check this, we've got 4 on the bottom, 5, 6, 7, and 8. Then we've got 9 and 10, 11 and 12, 13, 14, and 15 there. Okay? So again, 7 faces, 10 vertices. We plug it all in, we get edges is 15. Here's another one where we have a regular octahedron. Again, we're going to use Euler's theorem, which tells us number of faces plus number of vertices is equal to the number of edges plus 2. Number of faces, since it's an octahedron, that should be 8 faces. And there are, because there's 4 on top, 4 on the bottom. Number of vertices, we've got 1 on top, and then 1, 2, 3, 4 here. That makes 5 altogether. Plus 1 on the bottom is 6. Number of edges, we've got 1, 2, 3, and 4 for the triangles. Another 4 going around for that square, so that's 8. And then 9, 10, 11, and 12. So that gives us 12 plus 2. If you look, the left is 14. The right is also 14. That gives us our answer. Shows that since these are equal, it matches Euler's theorem. And again, this works for any polyhedron. So we've got 8, 6, and 12. We plug it in, we get 14 is equal to 14. Since this is a true statement, we know we've counted correctly. Alright, now we're going to look at a dodecahedron. Again, using this formula, number of faces plus number of vertices equals the number of edges plus 2. The number of faces, it's a dodecahedron, so a dodecagon has 12 faces. The number of vertices, we've got 1, 2, 3, 4, 5 here, and then we've got 1, so that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then if we look, the other side would have, this would be the very edge, so the other side would be a mirror image of this. So that's 16, 17, 18, 19, 20. So we've got 20 vertices. And then we look at the number of edges. We've got 5 going here, and then 6, 7, 8, 9, and 10 there. And then 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And then we count these, we'd have 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So there's 30 edges plus 2. Again, the back side of this would look exactly the same, so we're just doing double what was there. On this side we have 12 plus 20, which is 32. And on the other side we also have 30 plus 2, which is 32. So we're good there. Again, 12 faces, because it's a dodecahedron, has 20 vertices and 30 edges. That gives us 32 equal to 32, so it all checks out and we're good. Now we're going to look at cross sections. Basically, think of it as if you took a knife and you cut through this solid, what would be the intersection of this sort of pinkish area with the cube? In this case, it would be a square. If we look for part B, it's elongated this time, so this time it would be a rectangle here. Okay. If we look at this one right here, you look carefully and you can see that this edge right here and the edge up top, they're parallel, but one is bigger than the other, and so this looks like a trapezoid. And here's another one. You can see the pink section right here. The intersection would be a triangle. And for this cone, since we have it parallel to the base here, we can see that the cross section would be a circle. And when we have this hexagonal prism, since it's parallel to the bases, we can see that the shape here is a regular hexagon as well, or at least a hexagon. And that's it. Thanks.